So we're working on power series representation, and just to remind you guys of what you guys were working on, here's the ultimate goal. We are trying to turn some kind of interesting function into a over 1 minus r, okay? Which is what the geometric series converged to, is provided that the absolute value of r was less than 1. So this would be equal to the sum, and we've got the new and improved geometric series, which is n goes from 0 to infinity of a r to the n. We don't do n minus 1 anymore just to make it look good, but our summation starts at 0, so the exact same series. It just looks better when you started at 0 and having a nice power of n. Now, we talked about, well, this can be a little bit of a pain here because sometimes you may have to take the derivative of somebody to get him into this form, or integrate somebody to get it in this form, but you got to get it in this form so you can convert it into a power series representation. And this converges provided that the absolute value of r is strictly less than 1. So this will be by how we set up the interval of convergence on this guy. So this is the ultimate goal, is to turn things into this. Now, r is traditionally where your variable shows up at, but a could be a variable or it could be a constant with this stuff, okay? Now, to give you guys an idea of the power of this stuff, now if you write this thing out, this is a series. So if you write this guy out, you start with n equals 0, r to the 0 is 1, so you just get a, plus the next one you're going to get is a r to the first, plus the next one will be a r squared plus a r cubed plus da-da-da, and it's an infinite series. Now, why is this stuff so important? Well, last time you guys did this problem. Now, you proved through geometric series representation here that given the function f of x equals arctangent of x, arctangent of x had a problem. It doesn't look like a over 1 minus r. So what did you do, though? You took its derivative. And the derivative does look like a over 1 minus r once you fix it up. And then you figure out the a part is 1, the r part is negative x squared. So you basically plug them into your geometric series formula. Sum is n goes from 0 to infinity of a r to the n. You clean them up, and you got a power series for the derivative of the arctangent of x. Well, that's not the dude we wanted. So what did you have to do? You had to take this series and then go back and integrate him to get the original series. So you integrated the terms, and the summation stays the same. Remember, integrating x to any power, add 1 over add 1, so that's where you get the x to the 2n plus 1 over 2n plus 1 plus c. And you can figure out your constant integration because you should know that this is going to be a power series representation for the arctangent of x. And the arctangent of 0 is 0. So when you plug in 0, you get power series completely goes away because x is 0, adding up 0 a bunch of times is 0, plus c is 0. So that makes c equal to 0, which gives you the formula for the power series for the arctangent of x. And you could have, like I said, just written this guy out and just integrated each one of the terms, and you got the power series, quote, written out. Now, what's the big important deal about this thing here? Well, I came over here, and I want to show you an example of this thing here. So I put it over here and went to something called Desmos. Gives you a nice little graphing feature here. And what I'm doing up here is this red one up here is I'm actually graphing the power series as we've written out. Now, I wrote this one out, and I stopped after a while. So this is x minus x cubed plus x to the fifth, minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9 minus x to the 11th over 11 plus x to the 13th over 13 minus x to the 15th over 15 plus x to the 17th over 17. And I stopped because I got tired. Right? So classic, what we engineers do with a particular series. After a while, you catch a pattern and you put the famous dot, dot, dot. So sometime you're just going to cut this sucker off. Now, and then underneath it, I graph the arctangent of x. Now, if you look right in here, these are two graphs. This one right here is your series, right? This red one is actually the graph of the arctangent of x. So I just want to show you guys something rather. I'm going to blow this guy up. Now remember, this is an infinite series, because you keep on going forever. So if I come over here and put my little cursor, I didn't mean to do that. Okay. Oh, well, all right. So this. Hold on. The thing is very persnickety, so just to let you guys know. So I come over here, and I got this guy, and I'll copy him again and put him up here so I don't have to type all this mess over again. But I'm going to But the problem is it doesn't like power, so I got to come over here into my powers and fix them, because once you put two-digit powers, it messes it up. So it's 11 over that one. This one is x to the 13, and you can get to see what this thing's doing. When I put in the 13 and get rid of this 13 here, put in the 15 here, and get rid of the 15. Can you see this thing is actually going right there on top of? All right, so there's my arc tangent again. Just let me know. Catch a pattern on this thing. What's your next term? All right, so we went to catch a pattern. It seems to be the odd powers. So we're up to plus x to the 13 over 13 minus x to the 15 over 15 plus x to the 17th over 17. What's the next one going to be? Minus, right? All right, x to the, I'm going to have to put the template in here. Okay, what we do, we just do this. Come on, do what I tell you to do. Oh, okay, fine. There's ways of beating the dead horse to death. Let's go over here and do this one. Oh yeah, because I got to put it in this format. That's why. Just copy this one. Go back over here because you got to put it in LaTeX. I forgot that. So if I type this in, no, don't do this, you really. Well, the point I was trying to make here, we'll go back and do the same thing over again. All right, so let's go back and click on this one again. This thing, it is a pain in the royal rump to do this thing. All right, so go back over here and we'll type it in again. And then and you can't even cut, copy, paste. You got to do the old Control V on it. But there we go. So we're back over here and fixing it again. So that's the x to the 11th, x to the 13th. And you got to get rid of the 3 on this thing. And so here it is, extending it on. X to the 15th over 5. And if I get rid of this one right here, and if I just do this, what's happening here is as you change your function, this thing is changing, but your interval of convergence is right here. Right there, it looks like, not right now, it's between about -1 and +1. This graph is absolutely perfect, and then it starts to boom, and there is your difference right there. There's your tolerance. But as you add on more and more terms, this thing is going to extend out even further and further and further. Does that make sense? So this is what we're talking about in terms of a power series representation. You go, well, what's the big deal? Programming. How in the world do we take a handheld calculator, like the little TI-84 calculator right here? How in the world do we actually take this calculator right here, which is originally, it's an add, subtract, multiply, and divide machine. That's the original one. Pascal came up with this thing in the 1700s, the first add, subtract, multiply, divide machine. And turn it into things that do this. Let's graph the old y equals the arc tangent of x function here. How does it do this type of stuff? So when you actually, I forgot I'm in degree mode here. So zoom zip it. How does this thing do these type of aspects and stuff? Programming. So when you actually put stuff in your calculator, is there an actual arc tangent button that you plug the stuff into and it magically calculates arc tangent? Remember, this is a calculator. It's an add, subtract, multiply, and divide machine. So instead of plugging the x into the famous arc tangent, what your calculator does is it plugs it into the power series representation for that. And if you plug numbers into a power series representation, which is, in essence, we'll talk about this later, about a Taylor polynomial type thing here, you plug numbers into it, and look at it. Plug in 0.1 here. 0.1 cubed over 3 plus 0.1 to the 5th over 5, 0.1 to the 7th over 7, so forth. When you plug it in, when you power something up, all you're doing is multiplying it out so many times, and you're dividing and you're adding. Add, subtract, multiply, and divide is what you're doing. You're converting add, subtract, multiply, and divide to be able to do the transcendental functions. This is what your computers do, your calculators and the like. This is hugely important. And because of that, you guys need to know a big part of this thing down the road. Now, we also going to do this example right here. I think this was one. Cut copy. Let me get this one over here and show you another one. First off, let's do this one. Well, tell you what, this is the one we're about to do in just a second. I'll come back and do this one. So let's go back over here and do another example first. All right, so this is the one you guys did last time. The next example is this guy right here. Let's look at this, and I've also got a Desna example, as long as it doesn't mess up, because it is very persnickety. You get one little thing it doesn't like, it just throws it out. All right, so here we go. You're supposed to, WebWork problem, find a power series representation for the function f of x equals x divided by 8 plus x squared. And it's WebWork, so you're going to have to type it in just right. They want the first three non-zero terms. Now, what's nice about this one is it almost looks like the form of a over 1 minus r. So right now we got f of x is equal to x over 8 plus x squared. And the goal, remember, is to turn it into a over 1 minus r. So we can convert it into the sum as n goes from 0 to infinity of a r to the n. Okay? Provided this is your interval of convergence, absolute value of r is going to strictly be less than 1. So this is my goal here. Well, to be able to turn this x over 8 plus x squared into this, here's your algebra moves. The first thing you got to do is you got to get that 1 in there. So how do I convert an 8 into a 1? I'm going to multiply by 1/8. And what I do to the denominator, I'm going to do to the numerator. This will give me f of x is equal to 1/8 times x is x over 8 divided by, here I'm going to distribute 1/8 times 8 is actually the 1 plus x squared over 8. So the first thing you got to do is do that little algebra trick on getting that 1 in just that right spot. The next thing you need to do is you got to get the negative in the right spot. After you get the 1, you need to make it a minus. Well, this one's a plus, so what is a plus going to turn into? Minus a negative. So here we go. This would be equal to x over 8 divided by 1 minus negative x squared over 8. And now I can pick off my pieces. This implies that a equals x over 8, and r is equal to negative x squared over 8. As I mentioned to you before, a could be a constant, or it could be a term with a variable in it. It's okay. We're going to try to turn it into our power series representation. So here, this means my function is going to turn into the sum as n goes from 0 to infinity of a. A is x over 8 times r, which is negative x squared over 8 raised to the n power. This is your power series representation for this function, f of x equals x over 8 plus x squared. Two problems with this. First problem is this thing doesn't look nice. So algebraically, we got to clean this thing up. Second thing is, you got to tell me what the interval of convergence for whichever x's I can plug into this thing to make this thing converge. So, for the interval of convergence, we have here the absolute value of r has got to be less than 1. So this is the absolute value of r is negative x squared over 8 has got to be less than 1. Absolute value of a negative goes away. So this becomes x squared over 8 is less than 1. But to do that double-sided inequality on solving for x, you got to get rid of your powers. So what gets rid of a square? You're going to take the square root of both sides. And this will give you absolute value. The square root of x squared is just x, but square root of 8, I'm going to write him as the square root of 8, is going to be less than 1. Square root of 1 is 1. And then you do your double-sided inequality. Negative 1 is less than x over the square root of 8, which is less than 1. And then you multiply both sides by the square root of 8. You get negative square root of 8 is less than x, which is less than the square root of 8. This is your interval of convergence. So as long as you got x's between negative square root of 8 and positive square root of 8, these two functions are going to be the same thing, the original function and the power series. But now the next thing we're going to do is clean up the power series. Because let me tell you something, brother. You're going to see a lot of these problems. You'll see on the final exam, you're going to see them on the multiple choices, probably as well as the free response part. And the free response part, well, we'll give you most credit for this one, but on our multiple choice part, this is not going to be the answer in the lineup. You've got to clean up this stuff. So let's clean this thing up algebraically. So f of x would be equal to the sum as n goes from 0 to infinity of x over 8 times negative 1 to the n. I'm distributing my powers. This is negative x squared over 8 is negative 1 times x squared over 8. So I'm distributing my n. That gives me negative 1 to the n, x squared to the n, over 8 to the n. I distributed my n. Does that make sense? Now let's clean this guy up. This is the sum as n goes from 0 to infinity. I'm going to try not to skip any steps for you guys. This will be negative 1 to the n times x, but x squared to the n. Power to a power, what do you do with the powers? Multiply x to the 2n divided by 8 to the n times 8. When you multiply like bases, what do I get to do with the exponents? Add. Fourth grade math here. X to the 8 to the n times 8 to the first is 8 to the n plus 1. And one more last move. This is x, or officially x to the first times x to the 2n. When you multiply, you add exponents. So that'll be the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 8 to the n plus 1. This is your power series representation. Does that make sense? However, this is WebWork. And WebWork, as well as some of our tests, we want you to write out some terms. So how do I write out the terms on this thing? So f of x is going to be equal to, here we start with n equals 0. So n equals 0, n equals 1, n equals 2, n equals 3, ... Plug it in. Negative 1 to the 0 power is 1. 2 times 0 is 0 plus 1 is 1. That'll be x to the first. That'll be x. Divided by 0 plus 1 is 1. 8 to the first is 8. So my first term is x over 8. Now plug in 1. Negative 1 to the first is negative. 2 times 1 is 2, plus 1 is 3. This will be x cubed over 1 plus 1 is 2. 8 squared is 64. Does that make sense so far? Plug in 2. Negative 1 squared is positive 1. 2 times 2 is 4, plus 1 is 5. That'll be x to the 5th over 2 plus 1 is 3. 8 cubed, 8 raised to the third power is 512. Plug in n equals 3. Negative 1 cubed is negative. 2 times 3 is 6, plus 1 is 7. X to the 7th over 3 plus 1 is 4, and 8 to the 4th is 4,096. Yes, I'm using a calculator on the side here just to let you know I'm actually plugging in. Plus ... But WebWork asked for what? First 3 non-zero terms. So in WebWork, you would just type in x over 8 minus x cubed over 64 plus x to the 5th over 512. Does that make sense? Did I lose you guys anywhere? Now, go back to my little computer screen over here. See if I can get this guy. All right, this was my actual problem, right? And you see the graph of it right there, it's in blue. So I'm going to come over here, and if you look back at what we got typed in over here, this is my computer code. I took it out to a few more, but you'll see that it's the fraction x over 8, and the fraction x cubed over 8 squared, and it's minus, and it's plus. So this is actually completely written out for you guys, but I've written out quite a few more terms. All right, and this one I think is going to work a little better in terms of my programming. This guy here, and you'll notice, if I back it off a little bit, I got the same thing going on. And right here between this point and this point, they're right on top of each other. My error is showing up right over here. Does that make sense? However, what is my interval of convergence? I should have mentioned this on the last one as well, but that one completely crapped out on me. So look at the interval convergence. What was my interval of convergence on this thing? What was it? Negative the square root of 8 to positive square root of 8. Now the square root of 8 is 2.828, right? So if I come back over here to my graph, .828. So as you keep adding more and more terms, this thing is going to get closer and closer. Right here is where my error is showing up at. Does that make sense? But as I put more and more terms all the way up to the square root of 8, which is right in here, it's going to be right on top of it, because this is going to be the interval convergence between these two functions. Does that make sense? So instead of plugging stuff in here, I can plug stuff in here, and it will be quite happy. And you go, well, how does the calculator know? Well, the calculator doesn't take it out to umpteen thousand decimal places, because think about it. How many decimals are actually on your calculator? About 9. But there's a few more digits behind this that you don't actually get to see, so it's keeping up with it. But at about 12 decimal places is what this thing keeps up with. So once you start talking about x to the 19th over 19, and you plug in a decimal point into an x to the 19th, you're so far beyond 12 decimal places anyway, the calculator's just going to negate that. And so this is still approximating, but it's approximating out to 12 decimal places is what it does. It's classic computer science. That's why. How many of you guys are computer science majors in here? Computer engineering, computer science? All right, there you go. About a third of the class. Okay? Get used to this. And this type of manipulation that you're using, you'll see it again in differential equations. You'll see it again in some of your higher level mathematics classes, especially for you guys in electrical engineering. Circuits. Man, we do signals and doing series of to approximate the equations for those circuits all the time. Live and love this stuff. You are going to see this stuff again. All right. So, let's do another problem. Here's another WebWork problem for you guys. It says this. Follow the steps to find the power series for f of x equals 16 divided by x squared plus 2x minus 3. Okay? All right, so the first thing you were supposed to notice is, okay, we have a function, and that function happens to, the denominator happens to factor. So this is actually the same thing as 16 over x minus 1 times x plus 3, the denominator factor. So, and again, remember, we're doing power series representation. So your whole life in the world of 8.6 is, power series representation is, you want to convert formulas that look like a over 1 minus r into the sum as n goes from 0 to infinity of a r to the n minus, to the n actually, because we're going from 0 now to the n. The goal is to turn this, and the absolute value of r has to be strictly less than 1. This is the whole idea behind power series. You're using back to that first series we talked about, geometric series that you know so much about, okay? So, this guy is a quadratic in the denominator. It happens to factor. So I'm going to turn it into 16 over x squared plus 2x minus 3 equals a over x plus minus 1 plus b over x plus 3. What am I using here? Partial fractions. So that's what we're going to do. So you're going to take this 16 over that x minus 1 times x plus 3, and you're going to bust them into a over x minus 1 plus b over x minus 3, x plus 3. Notice it's a great time to review for the old final exam, partial fractions from chapter 6.3, if you remember. What's the next move I'm going to make? You want a clear denominator. So multiply by your common denominator of x minus 1 times x plus 3. And that's going to give you 16 is equal to a times x plus 3 plus b times x minus 1. And this one completely cancels the denominator, leaves you with a 16. This is a over here, this cancels. And with the b, this one cancels, so you're left with the other guy. Now, I'd like to use the annihilator method, so I got to solve for two letters, a and b. So I need two x numbers. What x numbers do you suggest I use? x is equal to 1, and x equals negative 3, the annihilator, the zero terms. Okay? So plugging in 1 into this guy, I'm going to get 16 is equal to 1 plus 3, which is 4a, plus b times 1 minus 1 is 0, completely cut off the b term. And that tells me a is equal to 4. Plug in negative 3, I get 16 is equal to a times 0, plus b times negative 3 minus 1 is negative 4. So divide by negative 4, b is going to be equal to 16 divided by negative 4 is negative 4. So a equals 4 and b equals negative 4. Does that make sense? Any questions? Partial fraction stuff. Now, here's the deal. Now hold those constants. This throws people off, so let me help you out with this WebWork, because you got one just like it on your WebWork set here. Now, we got these constants. Don't worry, we're going to throw those constants back in there later. But right now, they ask you to do this. They want you to find the first 4 terms of the power series representation for the following. So whether you screwed up A or not, you can still get credit for this guy. So we're just going to use them as 1 over x minus 1. Well, first off, it's in the wrong order. I want that constant in the front. So it's the same thing as 1 over negative 1 plus x. And again, to turn it into this a over 1 minus r, I need a 1 here. So what am I going to do? Multiply both the numerator and the denominator by negative 1. This will give me negative 1 over, here I'm going to distribute, that'll be 1. Negative 1 times a plus x is a minus x. And that's in the form of a over 1 minus r, which implies that a equals negative 1 and r equals x. So writing this as my power series, this will be the sum as n goes from 0 to infinity of a, which is negative 1, and r, which is x to the n power. Does that make sense? A over a times r to the n. But they want me to write out how many terms? 4 non-zero terms. But this starts with 0. So let me give you guys another hint on how to help this stuff out. All you want is 4 non-zero terms. Your first non-zero term typically shows up because this thing starts at n equals 0. So n equals 1, n equals 2, and n equals 3. I'm stopping at 3, but look, 1, 2, 3, 4, it's going to make 4 terms. So plugging in 0, this will be negative 1. X to the 0 is 1. 1 times negative 1 is negative 1. Plug in 1. X to the first will be minus x. Plug in 2. It will be negative x squared. Plug in 3, negative x cubed, but it's 1, 2, 3, 4 terms. So this would be my answer in terms of WebWork. Does that make sense? Questions? Now, we want to do the same thing for this guy. Convert him into a power series representation and write him down for the first 4 non-zero terms. So again, I'm going to put it in the other order. That'll be 1 over x plus 3, same thing as 1 over 3 plus x. But I want to get a 1 in this particular position right here. So I'm going to multiply both the numerator and denominator by 1/3. This gives you 1/3 divided by, here I'm going to distribute, this will be 1 plus x over 3. So I got the 1 in the position, but remember, we're looking for that a over 1 minus r. So once I get the 1 in the position, then I got to get the sign into the position. I have a plus. So to turn a plus into a minus, it's going to be minus a negative. So this will be 1/3 divided by 1 minus negative x over 3. This will imply that a is equal to 1/3 and r equals negative x over 3. So this will be the sum as n goes from 0 to infinity of a, which is 1/3, times r, which is negative x over 3 to the n. I'm going to clean this up because you need practice. So this would give you equal to the sum as n goes from 0 to infinity of 1/3 times negative 1 to the n times x to the n divided by 3 to the n. But that 3 on the bottom times that 3 to the n on the bottom in the denominator, when you multiply, even though in the denominator, you multiply, you add exponents. So this will give you equal to the sum as n goes from 0 to infinity of negative 1 to the n times x to the n divided by what? 3 to the n plus 1. 3 times 3 to the n is 3 to the n plus 1. Now that you've got this particular series cleaned up, because this is traditionally how we like to answer in terms of especially multiple choice questions on final exams and your 4th test here. So now, I'm gonna write down the first 4 non-zero terms, but the summation starts at 0. So here we go. N equals 0, n equals 1, n equals 2, n equals 3. 1, 2, 3, 4 terms. Plugging in 0, negative 1 to the 0 is 1. X to the 0 is 1. So it'll be 1 over 0 plus 1 is 1. 3 to the first is 3. Negative 1 to the first power is negative. That'll be x to the first, which is x over 1 plus 1 is 2. 3 squared is 9. Negative 1 squared is plus x squared divided by 2 plus 1 is 3. 3 cubed is 27. Negative 1 cubed is back to negative x to the 3rd power divided by 3 plus 1 is 4. 3 to the 4th is 81. Plus dot, 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 but here is my answer that I'm going to plug in on WebWork, the first 4 non-zero terms. Does that make sense? Now, the last part is this. They want you to write a power series representation for this guy right here. So the 16 over x squared plus 2x minus 3 is equal to a, remember what a was, it is 4 times that 1 over x minus 1, plus b, which is negative 4, times 1 over x plus 3. Here's my a, and here's my b being put back into my problem. This is what messes a lot of people up. So I'm trying to write it so you guys can see how the a and b are going to put in there. Because notice here, we didn't put the a and b. We just called him 1. These coefficients, they just held out front. And now I'm going to put them back. They're out front. But now I'm going to write the power series for this guy, which we came up with. This will be 4 times 1 minus x squared minus x cubed, plus da, 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 minus 4 times the power series for this guy, which is 1/3 minus x over 9 plus x squared over 27 minus x cubed over 81 plus da, da, da. So I substituted in the power series that we just created for these guys. Now I'm going to distribute and collect like terms. This will be 4 minus 4x minus 4x squared minus 4x cubed plus dot, 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 of course. And then I'm going to distribute the negative 4. Negative 4 times a third is going to be a minus 4/3. Negative times negative is going to be a positive 4x over 9. Minus 4 times x squared over 27 is going to be a minus 4x squared over 27. Minus 4 times a negative x cubed will be a plus 4x cubed over 81 plus dot, dot, dot. But we're not done. I want to combine like terms, clean this stuff up. Your constant. 4 minus 4/3. And I'm just going to go quickly on the calculator over here, just to let you guys know what I'm doing. 4 minus 4/3 is, convert it to a fraction, good, that'll be 8/3. Now combine your x's. I got a negative 4x and a plus a 4/9 x. That's going to give me minus 32/9 x. Yeah, question. Oh, it is, isn't it? That was a typo in that part. That makes it a negative 4. Thank you, darling. So this is negative 4 minus, what was it, 4/3. And that gives me negative 16/3. Thank you. That was a typo on my part. I lost the little negative sign off of this guy right here. He's negative 1. So when I put him in, he's negative 1, so that makes it a negative 4. They're all negative there. So that's negative 4 plus, say, negative 4/3 is negative 16/3. The x is negative 4x plus a 4/9 x is a negative 32/9 x. Now let's go with the cube, with the squares. I got negative 4, and I've got a minus 4 over 27. Minus 4 divided by 27. And that gives me a minus 112 over 27x squared. And then I got to do the cubes. The cube, I got a negative 4 x cubed there, and I got a plus 4 divided by 81 x cubed there, and that gives me a minus 320 over 81 x cubed plus dot, dot, dot. Now, this is classic web work, so you got to know the web work code. They're asking you to fill in the blanks. C0, C1, C2, C3, C4. Remember, C0 is your constant term. C1 is the term in front of the x. C2 is the term in front of the x squared. So if you happen to have like no x squareds, then C2 would be 0. Does that make sense? So these are the coefficients, and this is constant, this is the coefficient in front of the x, and sometimes you don't have these guys, and when you don't have them, make them 0. So for this one, we got seems to all the terms here. C0, your constant term, is what? Negative 16 thirds. C1 is negative 32 thirds. C2 is negative 112 over 27. C3 is negative 320 over 81, and that's what you type into your web work. Yeah? Over 9. I'm having a bad day up here. It's too early in the morning for me. I teach afternoon classes, and I come in here and help you guys out at 8:30 in the morning. Does that make sense, though? Just watch my constants. Trust me, I'll get this problem right if you guys keep working with me here. Yeah, just copy the numbers down. Don't pay attention to what I'm doing up here. Thank you. Does that make sense, though? Questions? It's not difficult, but it is tedious. All right. So here's one. Another classic WebWork problem here. But now, at this point, you're going to start using the power of power series that you guys know. All right? So it says this. Evaluate the definite integral, the integral of 2x minus the tangent inverse of 2x over x cubed as a power series. Enter the first three non-zero terms of the power series for the following series. So the first thing we want to do is find a power series for this guy. Now listen to my words because they're going to shock you. We love power series. Why do we love power series? Now you got to look at it from a computer science engineering perspective. They're easy to manipulate. See, I'm not going to try to figure out a whole new power series for this guy here. I'm going to use what I already know. I believe you have memorized, if you've done it, the power series for the tangent inverse of x. You remember what that dude was? You created him not that long ago. What was it? It was x minus x cubed over 3 plus x to the 5th over 5 minus x to the 6th over, x to the 7th, x to the 7th over 7th, it's the odd guys, plus dot, dot, dot. And just want to remind you guys, last problem you guys did in your last lecture, you created the power series for this guy. I'm just writing them down again because I have them memorized. Don't worry, you'll need to memorize about 5 of these guys. Don't worry, chapter 8.7 will explain which ones you need to memorize. This is one of them, okay? So that is the power series for the arctangent of x, tangent inverse. Does that make sense? But that's not the dude we want, Dr. Taylor. Don't worry about it. Watch this. What power series do we want for this particular function right here? We want the power series for the tangent inverse of 2x. Now repeat after me. We love power series. Go for it. Come on. That's right, because they're easy to manipulate. Remember this. It's going to help you out so much on that final exam. Don't recreate the wheel. What is the difference between tangent inverse of x and the tangent inverse of 2x? I just basically put a 2x in place of the x. Pure substitution. Think about that from a computer science programming perspective. Replace x with 2x. That's not a real difficult program. Does that make sense? So what do you get? I get replace x with 2x. So this will give me 2x minus 2x cubed over 3 plus 2x to the 5th over 5 minus 2x to the 7th over 7 plus dot, dot, dot. You see what I did? I just created a power series for the tangent inverse of 2x because I knew a power series for the tangent inverse of x. Now, of course, you want to clean them up. So here we go. The tangent inverse of 2x is equal to 2x minus 2 cubed is 8x cubed over 3. 2 to the 5th, better double check me, it's too early in the morning for this. 2 to the 5th is 32. That'll be plus 32x to the 5th over 5 minus 2 to the 7th is 128 x to the 7th over 7. And just for good measure, let's do one more. Always more is better than less. What would have been my next power series on this guy? It would have been x to the plus x to the 9th over 9. That would be plus 2x to the 9th over 9. So the next one would have been plus, and 2 to the 9th is 512 x to the 9th over 9 plus dot, dot, dot. So it's easy, so if you need one more, you can go back and pick them out. Always do more, because you'll see why in a second when I get you to manipulate this stuff. So, we want a power series for this guy right here. Well, once you get a power series for one part of your big function, you can create a power series for the whole thing. Let me show you. So to create a power series for 2x minus the tangent inverse of 2x over x cubed, this would be equal to 2x minus your power series that you just created for the tangent inverse of 2x, which came from the tangent inverse of x that you guys did last time. That would be 2x minus 8/3 x cubed plus 32/5 x to the 5th minus 128 over 7 x to the 7th plus 512 over 9 x to the 9th. And I can add some more terms if I need to. All over x cubed. Clean up your algebra. What is that negative going to do in front of all these terms you've written out? It's going to distribute. So I'm going to write it above there just to save some space here. So this would be 2x minus 2x plus 8/3 x cubed minus 32/5 x to the 5th plus 128 over 7 x to the 7th minus 512 over 9 x to the 9th plus dot, dot, dot. And notice what happens. Your 2x's cancel, right? But we're not done yet. So this is equal to 8/3 x cubed minus 32/5 x to the 5th plus 128 over 7 x to the 7th minus 512 over 9 x to the 9th plus dot, 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 all over x cubed. We want to clean that guy up. Again, I'm going to remind you of basic algebra. When you take a big polynomial in the numerator divided by a single term in the denominator, you're going to take this single term and put it under each term in the numerator. Does that make sense? And then you clean them up. So what is 8/3 x cubed divided by x cubed? 8/3 minus 32/5. What's x to the 5th divided by x cubed? When you divide, you subtract exponents. So what do you get? X squared plus 128 over 7. What's x to the 7th divided by x cubed? X to the 4th minus 512 over 9. X to the 9th divided by x cubed will be x to the 6th. Does that make sense? So this is my power series, but now what do they want me to do? Go back and ask the first 3 non-zero terms. So in WebWork, I would just type in these guys. Does that make sense? More is always better in case you ever need it. But now, look at the second part. You're supposed to integrate this guy, get a power series for this guy. So to integrate 2x minus the tangent inverse of 2x divided by x cubed dx would be equal to the same thing as integrating 8/3 minus 32/5 x squared plus 128 over 7 x to the 4th plus dot, dot, dot dx. I don't need this particular term. I can write them down if I want to, but they did say just write down the first 3 non-zero terms here. So, basic integral skills, good time for practicing calculus again for the final exam. What is the integral of 8/3 dx? 8/3 x minus, what is the integral of 32/5 x squared? Well, 32/5 is a constant. Integral x squared is x cubed over 3. So that gives you 32, 3 times 5 is 15, x cubed, right? Plus 128 divided by 7, x to the 4th. When you integrate x to the 4th, you get x to the 5th over 5. And so that gives you 128 over 7 times 5 is 35, x to the 5th. plus da, 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 and of course you have that plus C. They typically put that in front. So here is my answer that I'm going to type in on WebWork for that guy. But there was one more question in this particular problem. Question, yeah. I'm having a bad day here. Thank you. I say it, but I didn't write it down because I'm like 4 steps ahead here. Thank you. But does that make sense, though, this concept? But there's one more question on this guy. It asks you for the radius of convergence. Does that make sense? What would the radius of convergence be? Well, you have to go all the way back over here. You remember your arc tangent of x? Remember what that radius of convergence was? If you go back over on that radius of convergence, it was when the absolute value of x, because that's what you were having here, was less than 1. I'm going to go back and this was the absolute value of x is going to be less than 1. That was for the traditional tangent inverse of x. The radius of convergence was the absolute value of x is less than 1. But what we did up here was we replaced x with what? 2x. So what we're going to get here for the radius of convergence is the absolute value of 2x is less than 1. And whether you start manipulating or whatever, it's still going to give you the same radius of convergence. So and that radius of convergence comes from that tangent inverse of 2x, and that was, so write it down here, the radius of convergence, okay, calculating this. Well, the interval of convergence is where the absolute value of 2x was less than 1, which means negative 1 is less than 2x, which is less than 1, divided by 2 all the way down the line. So you get negative 1/2 is less than x, which is less than 1/2. This is what we call the interval of convergence. What does that make the radius of convergence then? Well, there's a formula, b minus a divided by 2, or if you think about a radius, the distance between the center to the outside edge. Between negative 1/2 and positive 1/2 is 0, and the distance between 0 and 1/2 is 1/2. The radius of convergence is 1/2. Does that make sense? And it came from replacing the x with the 2x in that arctangent thing. Does that make sense? Did I lose you guys anywhere? It's not hard. It's just incredibly tedious, but it also shows you what you should be in awe about is the power that this stuff has to be able to manipulate functions. And this is future mathematics classes that you guys are going to endure as you get into your majors and stuff. Okay? Here's another classic one. Use a power series to approximate the definite integral between 0 and 0.2 of 1 over 1 plus x to the 6 dx to 2 decimal places. Enter the first 4 non-zero terms of the power series for the following functions. All right. So again, back to power series. The whole goal is to do a over 1 minus r, okay, and convert that into the sum as n goes from 0 to infinity of a times r to the n, provided the absolute value of r is less than 1. So this is the whole thing. I keep reminding you guys of that. This is the geometric series. So, if I look at this first guy, as I blow this stuff up for you guys, okay, the first one, I got the 1 in the right spot. Problem is the sign. So this turns into 1 over 1 minus negative x to the 6th. Does that make sense? So, when I write this out, a is equal to 1, r is equal to negative x to the 6th. So plugging this into my formula, this would be equal to the sum as n goes from 0 to infinity of a, which is 1, r, which is negative x to the 6th to the n power. Clean them up. This is the sum as n goes from 0 to infinity of negative 1 to the n, x to the power you multiply 6n. But then here comes the classic web work as well as final exam and our next test. What we like you guys to do. Write out the first 4 non-zero terms. So the first 4 non-zero terms, we're going to start with n equals 0. N equals 0, n equals 1, n equals 2, n equals 3. That should give me 4 terms. So negative 1 to the 0 is 1. 6 times 0 is 0. X is 0 is 1. 1 times 1 is 1. Negative 1 to the first is negative. 6 times 1 is 6. That would be x to the 6. Negative 1 squared is plus. 2 times 6 is 12. X to the 12th. Plug in cube. Negative 1 cubed is negative. x to the 6 times 3 is 18, plus dot, dot, dot. So the first four non-zero terms is this guy here. Does that make sense? Now, part two, integrate. No problem there. So to integrate this guy is the same thing as integrating 1 minus x to the 6th plus x to the 12th minus x to the 18th plus dot, 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 dx. And that's going to give you, with the integral of 1 is x, minus the integral x to the 6th is x to the 7th over 7, plus the integral x to the 12th is x to the 13th over 13, minus integral x to the 18th is x to the 19 over 19, plus dot, 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 and of course you integrated, so you got your plus c. So to enter this thing in on WebWork, you would type in x minus x to the 7th over 7 plus x to the 13th over 13 minus x to the 19th over 19. 1, 2, 3, 4 terms. This is what you would enter in on your WebWork. Does that make sense? Now, what about this guy here? Now they want me to integrate. Well, we've already integrated, but I got bounds on this one. So when you got bounds, what's the difference between an indefinite integral and a definite integral? Well, an indefinite integral, you put plus c. A definite integral, you don't put the plus c, you put your bounds in your fundamental theorem. Plug in top minus plug in bottom. So this would be equal to x minus x to the 7th over 7 plus x to the 13th over 13 minus x to the 19 over 19, evaluated from 0 to 0.2. Fundamental theorem, plug in top minus plug in bottom. This would be 0.2 minus 0.2 to the 7th over 7 plus 0.2 to the 13 over 13 minus 0.2 to the 19 over 19 plus dot, 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 minus, when I plug in 0 for all my x's, guess what I get? 0. So now, put it on a calculator, and I get 0.2 minus 0.2 to the 7th divided by 7 plus 0.2 to the 13th divided by 13 minus 0.2 to the 19th divided by 19. And I end up getting 0.1999949 81715. I want to make sure this thing's correct to 6 decimal places. So you know what I'm going to do? I'm going to check them out. Math number 9. Integral between 0 and 0.2 of 1 divided by parentheses 1 plus x to the 6th dx is, how did I do? My point is, this is actually what the calculator is doing when you actually type in this interesting integral stuff. It converts this mess to a power series and then plugs the numbers into the power series and turns it into, because when you plug it in, all you're doing is add, subtract, multiplying, dividing, and that's what a calculator actually does. Does that make sense? Questions? All right. Chapter 8.7. Last chapter for you guys. Now, chapter 8.7 is known as is Taylor and Maclaurin series. That's right, they're named after us. No, it's actually my great-great-great-grandfather, Dr. Brooks Taylor, who came up with this in the 1650s after psoriasis and stuff. And I'm kidding, it wasn't my great-great-grandfather. I just want you guys actually look at this one. Wow. But no, it's real important stuff because think about it. It was in the 1700s that this stuff was actually developed, and we're using it today with so much of our computer science material. So, now, hopefully you watched the awesome pre-section videos on this stuff, and so these are the examples that we did, so please go back and take notes. But here, let's pick it up from the lecture. Here is the Taylor series formula. What Taylor discovered was the relationship between a function and its derivatives, all of its derivatives. And so, this is what Taylor discovered, that any function is equal to, you've got to have a function and you've got to focus on a particular fixed point within that function. We're going to call it x equals a. A is my fixed point. And so, a function is actually equal to f of a plus f prime of a times x minus a over 1 factorial plus f double prime of a times x minus a squared over 2 factorial plus f triple prime of a times x minus a cubed over 3 factorial plus dot, dot, dot. Okay? And you can write this as a formula, a series. It's the sum as n goes from 0 to infinity. The 0 is your not derivative. N equals 1 is your first derivative, so forth. So n equals 0 to infinity of the nth derivative of a times x minus a to the n over n factorial. Now, if you go back and look at Calculus 1, we did a bunch of stuff called linearization. That was the beginning, actually, of Taylor series. But the linearization, you had to have the slope of the tangent line, which is your first derivative. You plugged in the point, 1 factorial is 1, and you had to have your y-coordinate. And if you look at this guy, this is the equation of the tangent line. But there's more to it. There's also the second derivative, the third derivative, so forth and so on. So, this is how you develop a series is from its derivatives. Look at this example. Find the Taylor series representation for f of x equals cosine of x centered at x equals pi halves. Okay, they gave you a. So, the first thing you want to do is write out your function and a bunch of derivatives. So here we go. Calculus 1 at its best. Let's take derivative. What is the derivative of cosine of x? Very good. Negative sine of x. What is the second derivative? What's the derivative of negative sine of x? Well, negative is a constant. Derivative of sine of x is cosine of x. You guys are awfully quiet back there on these derivatives. This is Calculus 1, but don't get them confused with the Calculus 2 integrals because they're backwards. All right, so what is the derivative of negative cosine of x? Well, negative is a constant. What's the derivative of cosine of x? Well, it's negative sine of x, which makes it back to sine of x. What is the fourth derivative at x? What's the derivative of sine of x? Cosine of x. All right? And you never stop on a 0. Now, what do you think? How does he stop on a 0? Remember, we're going to take all these functions and plug in my centering point, pi halves. For you degree people, 90 degrees. It's pi halves, radians, right? What's the cosine of pi halves? 0. Never stop on a 0, so at least one more term. So what is my fifth derivative? What is derivative of cosine of x? Now back to it again. Negative sine of x. Now, we're going to evaluate my derivatives at your centering point. So f of pi halves, that would be the cosine of pi halves, and the cosine of pi halves was what? 0. F prime of pi halves, that would be the sine of pi halves, and the sine of pi halves, the sine of 90 degrees, is 1 times that negative makes it negative 1. F double prime of pi halves. What's the cosine of pi halves again? 0. Negative that's still 0. Third derivative. What is the sine of pi halves? 1. Fourth derivative. What is the cosine of pi halves? 0. And never stop on a 0, so that's how we got to go up to the fifth derivative. And what is the negative sine of pi halves? Well, the sine of pi halves is 1 times negative makes it back to negative 1. Now, I'm going to write this in this particular formula. My function is the cosine of x. It is actually equal to f of a. F of a, f of pi halves, is 0 plus f prime of a. F prime of pi halves is negative 1. Negative 1 times x minus a, which is pi halves, over 1 factorial. I want to literally see I'm plugging this into my formula. Plus f double prime of pi halves. The second derivative of pi halves is 0 times x minus pi halves squared over 2 factorial plus f triple prime, third derivative at a, at pi halves is 1 times x minus pi halves cubed over 3 factorial plus fourth derivative. Now after that, we don't come, but you got to catch a pattern on it. Well, my fourth derivative is 0. That'll be 0 times x minus pi halves to the fourth over 4 factorial plus the fourth derivative, which is -1. So the fifth derivative, -1, which is -1 times x minus pi halves to the fifth power over 5 factorial plus ... But you're right. Beauty of the sine and the cosine stuff is at these centering points, half this stuff is 0. So you don't have to write that guy. That's gone, that one's gone, and that one's gone. So your Taylor series, also known as a Taylor polynomial, for this particular function, cosine of x, centered at pi halves is negative x minus pi halves over 1 factorial plus x minus pi halves cubed over 3 factorial minus x minus pi halves to the fifth over 5 factorial, and you can catch a pattern after that, plus ... And it goes on forever, so it's an infinite series. Does that make sense? This is your Taylor polynomial centered at pi halves. And so this function and this guy centered at pi halves is exactly the same thing, and it goes on forever. So if I wanted to approximate this guy right here, cosine of x, what's the cosine of 1.5? What is the cosine of 1.5? I'm in radian mode here, radians, just to let you know. Cosine of 1.5, according to calculators, 0.07073720717. Does that make sense? How does the calculator do that? Well, let me show you. Instead of plugging 1.5 in here, let's plug it in here. What is negative, parentheses, 1.5 minus pi divided by 2 divided by 1 factorial. What's 1 factorial? 1, I'm not going to put that in, plus, parentheses, 1.5 minus pi divided by 2 cubed divided by 3 factorial. 3 factorial is 3 times 2, 1/6. Minus, one more term, 1.5 minus pi divided by 2 to the 5th power divided by 5 factorial. 5 times 4 times 3 times 2 times 1, 120. Okay? And let's see what I get there. What do I happen to get? The same thing that the calculator gave me when I actually typed in the cosine function on it. But what's the difference? Is when you actually plug it in here, you're taking a number and you're subtracting pi halves. And then you're negating that and dividing. Then you're going to add, plug in a number, minus pi halves, and you're going to cube it, which means multiply it by itself 3 times, and divide by this number. Minus 1.5 minus pi halves. And 5th power means multiply times itself 5 times, divided by 120. It's turning it into a process of add, subtract, multiply, and divide. We got real smart on how we're manipulating our calculators, which is an add, subtract, multiply, and divide machine, to be able to do things like cosine of 1.5. Understand the programming aspect of this is huge. Does that make sense? All right. Now, this is called a Maclaurin series. Now, let me explain to you guys the way I look at Maclaurin series. Maclaurin got a free PhD off of Taylor. Taylor series is the big series. At any value of A, you plug in A, that centering point, and you get yourself a big old Taylor polynomial. A Maclaurin polynomial is a Taylor polynomial centered at, what would the easiest number we can plug into any function? Yeah, that's it. So a Maclaurin series is a Taylor series centered at 0. So, but here's the deal. We don't tell you, hey, find the Taylor series centered at 0 of this particular function. We're going to say, find the Maclaurin series. It's implied that your centering point is going to be 0. So it will clean up your Taylor series quite nicely It's f of 0 plus f prime of 0 times x minus 0, great, over 1 factorial plus f double prime of 0 times x squared over 2 factorial, f triple prime of 0 times x cubed over 3 factorial plus, and you got a nice little formula. It's the sum as n goes from 0 to infinity of the nth derivative of f evaluated at 0 times x to the n over n factorial. So here is a Maclaurin series, and it is a power series that you guys need to memorize. It's the Maclaurin series for the famous e to the x. Here we go. All right, so e to the x. We're going to write out our Maclaurin series. The function's e to the x. What's its derivative? Don't hurt yourself. What's the derivative of e to the x? E to the x. But I don't think you guys knew that. So let's take the second derivative of it. What's the derivative of e to the x? That's still e to the x. And why not? The third derivative of e to the x is e to the x. I think I can get your pattern after a while. The derivative of e to the x is e to the x. But now remember, this is where most students are going to screw this mess up. You have to take your function and plug in your centering point, your a. Well, with the Maclaurin series, a equals 0. So you don't type in e to the x's all over this thing. You don't know, you don't do it. These are functions evaluated at a point. These will be numbers. So f of 0 equals e to the 0, which is 1. F prime of 0, which is e to the 0, which is 1. F double prime of 0 is e to the 0, which is still 1. And last one, f triple prime of 0 is e to the 0, which is 1. So all my derivative coefficients are going to be 1s. So when I write this thing out, e to the x, this is going to be equal to f of 0. F of 0 is 1, plus f prime of 0, which is 1, times x over 1 factorial, plus f double prime of 0, which is 1, times x squared over 2 factorial, plus f triple prime of 0, which is 1, times x cubed over 3 factorial, plus dot, dot, dot. Well, if you clean this up, your Maclaurin series for e to the x is 1 plus x over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus dot, dot, dot. Tell you what, help me write out an actual series formula for this thing. What's my series formula going to be? Well, you're starting with n equals 0, but look at your powers. The power on the x's is actually n. It's x to the n over n factorial. This is actually the Maclaurin series for the famous e to the x. I know you're worried. Well, what about that 0? You can't divide by 0. Now, be careful. This is not 0. This is 0 factorial. What is the definition of 0 factorial? It's equal to 1. Okay? So x to the 0 is 1. 0 factorial is 1, and 1 over 1 is where the 1 point comes from. Then you plug in n equals 1. That'll be x to the first over 1 factorial plus x equals n equals 2, x squared over 2 factorial plus dot, dot, dot. Does that make sense? Now, this is why you need to memorize this. I know it's calculus too, but we make you memorize everything. But trust me, this is going to come back and haunt you big time on the final exam and your next test. Memorize this one. There will be 5 of them that you memorize. The famous Maclaurin series for 5 functions here. The reason for that is, look at our next problem. Find a Maclaurin series representation for g of x is equal to x times e to the x. No worries. If you can get a series for just part of your function, you can extend that to create a series for the whole darn thing. See, I'm not going to recreate and take a bunch of derivatives of this thing, because I use the product rule and all that good stuff. No. What you do, again, let's repeat ourselves. Series are easy to manipulate. We love series because they're easy to manipulate. Remember that. This is a game of now I can do problems in 10 seconds or less. Here's a 10-second question here. Find the Maclaurin series for g of x equals x times e to the x. Well, this is going to be x times, well, I got a Maclaurin series for e to the x. See your last problem. That is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. Right? Well, let's clean that guy up. All I'm going to do is distribute the x through the last series. That's going to give me x plus x squared over 1 factorial plus x squared over 2 factorial. I'm sorry, x cubed over 2 factorial plus x to the 4th over 3 factorial plus dot, dot, dot. Does that make sense? Wait a minute. Sometimes they want me to write out the series formula. Well, that would be x times the series formula for e to the x is the sum as n goes from 0 to infinity of x to the n over n factorial. And so when we clean it up, you'll pull the x on the inside. And when you multiply, what do you do with the exponents? Add them. So what do you get? The sum as n goes from 0 to infinity of x to the n plus 1 over n factorial. Once you got part of your function as a series, you can extend it to create a series for the whole thing, and you don't have to recreate the wheel. Don't get me wrong. For you people that are just hard-headed, knock yourself out. You want to take your function as x e to the x and take the first derivative, second derivative, third derivative, fourth derivative of these things, product rule the whole time, then plug in 0, and then crunch out this particular formula. You know what you're going to get? This dude right here, okay? It's easy to manipulate. Does that make sense? So speaking of the 5 functions you need to have memorized, one of them we've already used before, now we've used the second one, are these guys here. Now this one right here, the tangent inverse, you remember this guy? It was x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. We used him in the last section because we derived him from the power series representation. But as a series, it's the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. The 2n plus 1 is the fact you're getting all these odd powers. Odd powers divided by the odd coefficient. Okay? Here's a classic one right here from your power series representation. The famous Maclaurin series for 1 over 1 minus x is the sum as x goes from 0 to infinity of x to the n, which is 1 plus x squared plus x cubed plus dot, dot, dot. This one right here, e to the x. E to the x is, we derived that one ourselves, that's the sum as n goes from 0 to infinity of x to the n over n factorial plus, which is equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. Sine of x. Sine of x is the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, which gives you x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus dot, dot, dot. Cosine is the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n over 2n quantity factorial. That is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus dot, dot, dot. Yes, memorize them. However, key to math, key to life, catch a pattern. Catch a pattern on these things. Number 1. E to the x should not be that difficult. It's x to whatever power over n factorial. Okay, x squared over 2 factorial plus x cubed over 3 factorial, dot, dot, dot. Okay, so it's 1 plus x over 1 factorial plus x squared over 2 factorial. This 1 over 1 minus x is 1 plus x. These are the easy ones here. Where most people get concerned is when I start chunking sine and cosine in them. But you guys remember from, I don't know, junior high school and high school about sine functions and cosine functions? Sine function is considered to be an odd function. Cosine function is an even function. Odd functions are symmetric with respect to the origin. Even functions are symmetric with respect to the y-axis. But they're odd and even. Sine is odd. Look at the powers. It's x to the first, x cubed, x to the 5th, x to the 7th over the same factorial. And it alternates, so it always starts off on a positive foot. So this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. You with me so far? But look at them. They're the odd powers. Now switch over to cosine. What's cosine? Even. And remember, 0 is considered to be an even number. So you get your constant because that's the x to the 0 power. So it's 1 minus even powers. X squared over 2 factorial plus x cubed over 4 factorial minus x to the 6 over 6 factorial. It's the even powers, and it alternates. Now, do you guys remember tangent? Look at the connection. Sine and tangent are almost the same series. What's different? One slight thing which makes a completely different function. That factorials are missing. So if you memorize tangent, you got sine for free. Just chuck a factorial in these and the powers and you win. Key to math, catch a pattern on these guys because you saw what we did in the last problem. We're going to manipulate them. So you see the next problem, which I'll do, or Desiree will do next time, x times cosine of 2x. We're going to take the cosine and plug in 2x's for all these things, clean it up, and then distribute an x throughout of it. Look at the next guys. Well, the next ones are going to be your binomials, but if you switch over here to some of these power series and stuff that you're going to be doing, look at these kind of problems. X times the tangent inverse of 4x. X cubed e to the negative x squared, negative x over 2. And you're supposed to find a Maclaurin series for these guys given about 4 terms or something, 3 non-zero terms or something like that. This is exactly what we've been doing. Does that make sense? Study hard and see you guys next time.